So, what is measurement uncertainty again? And what are the main contributors of uncertainty in a weighing device? I'm going to go over in these next few slides the various parameters of uncertainty of measurement and how they actually look on a graph to show you what, in a visualization, when you weigh on a balance all the different parameters that are having an effect on that uncertainty. So, there's a nominal property called readability. That's the difference in value that the scale is able to register in weight. So, for example, if you get a 4-place analytical balance, your readability is going to be 0.1 milligrams. That means that that particular analytical balance has the ability to determine the difference of plus or minus 0.1 milligrams of weight. But there's 4 other parameters that encompass the majority of the uncertainty of measurement. You have sensitivity, nonlinearity, corner load, or another word would be eccentricity, and repeatability. So what exactly do these look like? This is a graph of a perfect scale, meaning that this line right here, which will have a curve of 1, every time you put anything on this balance, whether it's from no load to full load, what you see on that instrument, on that display, is going to be the exact measurement that you're going to be getting, the exact weight that you're trying to establish. But no scale is perfect, ever. Even after a calibration, no scale is ever going to be exactly perfect. So let's talk about the difference of particular uncertainty of measurement parameters. Again, the nominal value or parameter would be readability. Again, the difference that the balance or the scale can determine in a mass, in a weight. You see here that depending on the indication of the scale, you're going to have various readabilities. When it comes to modern weighing instrumentation, typically speaking in a laboratory, you're going to have anywhere from 7 decimal place ultra micro balances all the way up to plus or minus 10 kg in some instances for some larger floor scales. But that's the easy one. Let's talk about sensitivity. Again, this line here is the perfect scale, but every scale or balance is not perfect. Sensitivity is the deviation of what you're actually seeing on the balance compared to what the actual value is. If you were to take a weight near the capacity of your balance and drop it on there, let's say you have a 220 gram analytical balance, and you put a 200 gram weight on that. There's going to be an actual difference between what that value is showing you on that analytical balance and what the real value is. This is a straight line, and we're going to talk about sensitivity when it comes to routine testing here in a few slides. The second parameter is what's called nonlinearity. Nonlinearity is actually the value of that particular weight compared to a known mass and what is being displayed on the balance throughout the entire weighing range. This is not a straight line, and it's actually a deviation throughout the entire linear curve. The next parameter is eccentricity, or corner load. This right here is an example of a weigh pan. Depending on where you place your sample, top left, top right, bottom left, bottom right, or center, you're going to have different values. So it's always important to weigh in the center of your weigh pan. However, due to varying weighing practices, that's not always the case. But it's important to note that if you do move your sample around the weigh pan, you very likely will get different results on that display. The last one, probably the most important one, especially when it comes to smaller weights, is repeatability. This is the balance's ability to get the same measurement when you do multiple weighings with the same technician, doing the same technique, with the same sample that you're trying to weigh. You can see here that this particular example, there was 260 gram weight that was weighed 10 times. And every time it was weighed, there was a deviation. So all of these parameters of uncertainty between the nominal value of readability, sensitivity, eccentricity, linearity, and nonlinearity all go into this lovely equation up here to establish the total uncertainty of measurement. This is lagging behind a little bit, bear with me. So, The measurement uncertainty has a very particular behavior when it comes to how it is established throughout your entire weighing range. Right here you can see the absolute measurement uncertainty in kilograms for this particular example. As the weight increases and the measurement uncertainty increases up here on this axis. So how does that interpret the relative measurement uncertainty, as it's called? This line here is the relative measurement uncertainty of your sample. When I say relative, that means the level of uncertainty for the sample that you're weighing. If you notice, as the sample decreases in size, the uncertainty increases exponentially. And the relative measurement uncertainty equals the absolute measurement uncertainty, again, which is this line here, divided by the weight of what you're weighing. So, we're going to focus now on minimum weights and what we call a safety factor. Minimum weights were very commonly used when it comes to USP requirements in a pharmaceutical environment. But in modern laboratories, minimum weights are now being applied to any application in all environments of your facility, whether it's using a floor scale, where your process tolerance is much higher, or if it's weighing APIs on a microbalance, where your process tolerances are going to be much stricter. Your accuracy limitation, right here, will equal your minimum weight. And what I mean by that is that when you establish a minimum weight on your instrument, that is the lowest that you can possibly weigh without going beyond that process tolerance. And this, again, is called a minimum weight. If there is any weighing that's done below that minimum weight, you're not going to be in compliance because you're not going to be meeting your process tolerance. And in turn, it will lead to inaccurate weighing results. Your minimum weight increases as your process tolerance gets tighter. So, as an example here, you have a minimum weight for 1% tolerance. On this axis here, in terms of kilograms, you're able to weigh very low. But if you notice, as the process tolerance gets stricter and more stringent, your minimum weight increases. To give an example, if your minimum weight is 1%, let's say for an ISO 17025 environment, you can weigh a factor of 10 less than if your minimum weight requirement and process tolerance is 0.10%, which is the new USP Chapter 41 minimum weight. So, the concept of minimum weight, this is coming from Chapter 1251, which is a new chapter in USP general chapters for weighing. The minimum weight of your sample can be expressed by M min equals K times S divided by the required weighing tolerance. Very simply put, for a process tolerance of 0.10%, which is for USP environments, your minimum weight equals 2,000 times S, where S is the actual standard deviation of your measurement of uncertainty, or in this example, for repeatability. If you had a process tolerance of 1%, that equation would equal 200 times S. If your particular process tolerance was 10%, that equation would equal 20 times S. So as you can see, the higher your process tolerance goes, the lower you're actually able to weigh on that particular instrument. Now, just for purpose of this conversation, USP is the only regulatory compliance agency that actually has a specified process tolerance, which is 0.10%. Even ISO doesn't state a particular weighing tolerance for your applications. All your weighing tolerances should be established by the end user based, again, off of risk analysis of your particular application. So, what if you're not in a USP environment? You still should establish a minimum weight, and we'll go over again the reasons why here in a few slides. So how do you test for repeatability to establish the minimum weight? Again, S is the standard deviation of your repeatability test. You perform a repeatability test by taking a known weight, placing it on your scale or your balance, and weighing it 10 times without zeroing it, and doing a standard deviation of 2. That will determine your repeatability on the instrument, which is used to establish your minimum weight.